As I was drawing an atomic tree on my iPad, lost in the world of electrons and orbits, my husband glanced over, puzzled, and he asked if I was branching out from physics to art. Little did he know, I was just trying to find a new way to visualize nanomagnetism. And here's what I came up with. Ever feel lost in a dense forest of atomic structures and electron arrangements? You're not alone. It's like being in an enchanted forest, where each tree holds secrets to unlock. But don't worry, today we navigate this forest together. In the quest to demystify nanomagnetism, or magnetism in general, we must first explore where it all begins. Understanding the electrons' dance around the nucleus is key to unlocking the mysteries of magnetism, and it is essential for mastering chemistry and quantum physics. Today, we'll lay the groundwork for exploring nanomagnetism later in this video series. Let's turn the abstract into the accessible with a mnemonic device, a vivid atomic tree, to help remember the atomic hierarchy. Now imagine atomic shells as main branches, subshells as twigs on those branches, and orbitals as leaves growing on the twigs. This familiar imagery can help cement complex atomic concepts in your mind. From shells to subshells to orbitals, let's watch our atomic tree come to life. As an example, let's plant a copper tree. As we grow our atomic tree, envision the principal quantum numbers as the main branches, stable and secure at the bottom, more dynamic at the top. Each branch corresponding to a principal number n. N defines the energy level, or shell, with lower branches cradling the most stable, least energetic electrons, and as we climb, the branches with higher n values sway more, indicating electrons with higher energy and less stability. Now, let's grow some twigs on our branches. The principal quantum number n defines how many twigs a branch can grow. We can identify the twigs with the angular momentum quantum number L. L can take on the values between 0 and n minus 1. For example, if n equals 1, L is 0. So for n equals 1, there is only one value of L, one twig for this branch. For a branch n equals 2, L can take on the values of 0 and 1. So there's 2 L values, 2 twigs on the branch 2, and so on. Now the angular momentum quantum number L shapes the twigs, or subshells, and specifies the type, S, P, D, etc., where S corresponds to L equals 0, P has L equals to 1, and D has L equals to 3. We can distinguish the twigs on a branch by its L number. Now let's grow some leaves on our twigs, with leaves representing the orbitals. Each leaf can be identified by its magnetic quantum number m sub L. M sub L ranges from minus L to plus L, including 0. The number of leaves, or orbitals, on each twig is determined by the type of a twig. For example, S twigs bear a single leaf. Since L equals 0 and m sub L equals 0, only a single value of m sub L is possible for this L. The P twigs have 3 leaves, since L equals to 1, and so m sub L takes on the values of minus 1, 0, and 1. Therefore, we get 3 m sub L values for this L, and so on. However, leaves positioned on a twig are not random. Imagine invisible forces, like magnetic fields in our world, permeating the forest. These are the guides for our magnetic quantum number m sub L, aligning each leaf or orbital meticulously in space, setting the exact position for each leaf on the twig, ensuring that the orbitals are spaced just so, creating a harmonious pattern around the nucleus. Each leaf houses a maximum of 2 electrons, or you can call them little tree spirits if you want. They differ by their spin, up or down, but they are living in harmony on a leaf, thanks to the Pauli exclusion principle. Spin quantum number m sub s can take on the values of plus or minus 1/2, and it helps to further distinguish between the 2 electrons on a leaf, or in an orbital. Now let's pick a single leaf and write down a set of quantum numbers for one of its 2 electrons. Just glancing at this diagram, we can see that it lives on the branch number 3, on a twig labeled as L equals 1, which means it is a P subshell, and on a leaf labeled by ML equals 1. It is pointing up, so its spin quantum number is 1/2. And that's it. This is a set of quantum numbers that gives us the unique address or coordinates of this electron living in this copper tree. With our atomic tree blossoming, we told a tale that not only aids memory but also sets the stage for deeper exploration into how these tiny structures give rise to the magnetic properties we'll soon delve into. crafting this atomic tree tale has transformed my own understanding of the atomic structure and the hierarchy that electrons follow around the nucleus. Now go on, choose your own chemical element and plant your own atomic tree. Until next time, keep those electrons in check and your curiosity high.